This is our sun. And this is our sun's magnetic field. Most of us think about the sun as light, heat, and radiation, but the sun is also a complex magnetic object. Its surface and atmosphere are filled with magnetic structures, some that loop back down into its surface, and others that open far into space. The important part is that its magnetic field does not stay at the sun. Not only does it reach Earth and all of the other planets, but it extends far beyond them. And that happens because the sun is constantly releasing plasma into space. That plasma is called the solar wind, and that's a stream of charged particles that's blowing in all directions from the sun. And because those particles are charged, they can carry the magnetic field with them. So as the solar wind expands outward, it drags the magnetic field out into space. In fact, the solar wind keeps dragging that magnetic field farther into space until eventually the pressure from the solar wind balances against the pressure from the interstellar medium. This is what we call the space in between stars. All of this forms an enormous cavity that we refer to as the heliosphere. If you want to learn more about the heliosphere specifically, then you can see the video I've made on that using the link in the description below. So Earth is not just sitting in sunlight. It exists within a stream of plasma and magnetic fields emanating from the sun at all times. By the time that magnetic field passes Mercury and Venus and reaches Earth, the space physicists refer to it as the interplanetary magnetic field, or the IMF for short. That name sounds technical, but the concept is relatively simple. The IMF is the sun's magnetic field carried outward through the solar system by plasma that we call the solar wind. And we Earthlings, along with all of our electronic technology, are bombarded by it every single day. So if the IMF is the sun's magnetic field, and that's carried out by the solar wind, which is a plasma, the natural next question might be, why does plasma drag magnetic field with it in the first place? And the key is that plasma is not like neutral gas. Here on Earth, when we talk about the wind, we're talking about air moving around through the atmosphere. That air is made up of neutral particles, and they push things around mechanically. But because those particles are neutral, they're not affected by electric fields and magnetic fields. And as you now know, the solar wind is a plasma, and it's made of charged particles, mostly protons and electrons. And that distinction is important because charged particles respond directly to electric and magnetic fields. So when plasma moves through space, it doesn't behave like a neutral gas. It responds directly to the sun's magnetic field, or the IMF. In space physics, we describe this relationship by saying the sun's magnetic field is frozen in to the plasma of the solar wind. That phrase doesn't mean the magnetic field is literally frozen in like ice. It just means that on large scales, the plasma and the magnetic field tend to move together. So as the solar wind expands outward, that magnetic field comes along with it. And that's the real physical reason why the sun's magnetic field can extend far beyond its surface. And it's also why the IMF is not just a small detail. It's actually a part of the whole solar system itself. Every parcel of solar wind carries information about the sun's magnetic field along with it, its direction, its strength, and how unorganized or organized it happens to be. To put it simply, when the solar wind reaches Earth, it brings the sun's magnetic field along with it. And that magnetic field becomes one of the most important factors for how the space around Earth responds to the solar wind. So now you know the IMF is the sun's magnetic field and that it's carried out throughout the whole solar system by the solar wind. But that doesn't mean that it looks the same everywhere. It has measurable properties. It has strength, direction, and variability. The strength of the IMF tells us how intense the magnetic field is itself. Near Earth, we usually measure the magnetic field strength in units that we call nanotesla. And this is much smaller than the magnetic field strengths that you might find in labs on the surface or closer to large planets like Jupiter. But of course, in space physics, small does not necessarily mean unimportant. Even weak magnetic fields can strongly influence charged particles moving through space. The direction of the IMF tells us where the sun's magnetic field is pointing, or how the field lines themselves are physically laid out. In general, they point towards the sun or away from it, but they can also be pointing north or south relative to Earth, as well as side to side. And each of these directions matters for how the solar wind interacts with objects that it encounters, such as planets or comets. In some regions of the heliosphere, the sun's magnetic field points generally towards it, and in other regions, it points generally away from it. We call these the towards and away magnetic sectors, and they become important when we want to talk about something called the heliospheric current sheet. Along with measurable strength and direction, there's also variability. In reality, the IMF is constantly changing, and that's because the solar wind isn't perfectly smooth. It changes due to things like how the sun is rotating, the presence of solar eruptions like coronal mass ejections, and even because of periods of faster and slower solar wind speeds. This is where faster moving plasma physically runs into slower moving plasma traveling ahead of it. To put it simply, the IMF is not a uniform or static magnetic field. It is a highly complex magnetic environment that is constantly changing. And when spacecraft measure the IMF near Earth, they're measuring how strong it is, which directions it's pointing in, and how much it changes over time. So let's recap what we've learned here so far. The IMF is the sun's magnetic field. That field is carried out far into space by the solar wind. The solar wind is a stream of charged particles that we call a plasma, and all of this is constantly changing. And this really means that the IMF matters long before it even reaches Earth, because it tells us how much this magnetic environment is changing throughout space. The full extent of this magnetic environment, which is led by the solar wind, carves out a cavity in space that we call the heliosphere, and it extends far beyond our planets. When the IMF is relatively weak and steady, Earth will experience generally quiet space weather conditions. But when the IMF becomes stronger or more disturbed, or it changes directions rapidly, the space around Earth can be disturbed more significantly. And this is precisely why space physicists care about the IMF's direction, strength, and variability. These properties give us clues about what the solar wind is doing before it reaches Earth, and it enables us to predict how that might interact with our own magnetic field. They can tell us if the sun's magnetic field is organized neatly or if it's filled with lots of structure. They can tell us whether Earth is currently passing through the towards or away magnetic sectors. And they can reveal whether a solar eruption or a compressed magnetic structure is headed our way. So the IMF is not just an abstract idea. It's actually one of the best ways that we have to study how the sun impacts Earth and the rest of the solar system. And that brings us to our next question. If the IMF is the sun's magnetic field, and that's carried out by the solar wind, what does the field actually look like? Because it's not shaped like straight lines pointing away from the sun. The sun itself actually rotates in a very special way. And because the solar wind flows out while it does this, the magnetic field gets twisted into one of the most important shapes in the entire heliosphere, the Parker spiral. Thanks for hanging out with me today. This is the first in a 3-part series about how the sun's magnetic field actually impacts Earth. If you enjoyed this, please leave me a comment below, hit like, and share this with somebody who you think might also enjoy it. Cheers.